have some more examples about the complement of sets, the union of sets, and the intersection of sets. And we're going to do some vocabulary. And start to talk about interval notation. Okay. So we talked about the universal set being the entire space that you're working in. And it's a capital U. This time we have 1, 2, 3, 4, 5, 6, 7 inside of your set. We have one subset, we'll call it capital A. Inside of your set, we have 2, 3, 4, 6. And we just want to find the complement of A. A complement is everything that's not in A. So not 2 or 3 or 4 or 6. And we were drawing Venn diagrams, so we will do a sketch of the space. Is A. A has 1, 3, 4, 6. And then the universe contained 1. A has 2, 3, 4, 6. If you ever notice a mistake, you could please share in the chat or just like let me know. That way we can fix it together. 2, 3, 4, 6, 1, 5, 7's on the side. Is A complement. Okay, new universe. It has 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so start the set with a curly bracket. Your elements start at 0. Close the set. We have 2 subsets, A and B. Okay, so the set starts and it contains 0, 1, 2, 3, 4, 5. Close your set. B is going to contain 0, 2, 4, 6, 8. So all the even numbers from the universe. So the universe is going to be our subsets A, B. So first, find anything in common, like 0, 2, 4. So where A overlaps with B is where they share the same elements, and those shared elements are 0, 2, and 4. A contains 1 and 3, but those elements are outside of B. B has 6 and 8, but A does not, so it's going to be here. Check for everything. 1, 2, 3, 4, 5.
It's missing 5.
Wait, 5 is in A. 5, 6. We need 7. 8. So let's see. Okay, the first set we'll look for is A intersect B. A union B. A complement. B complement. Okay, so this is where you have A elements that are in A and B. This is for or, so it's in A or B or both. This is not in A and not in B. Start here. Start a set. Using your Venn diagram, it's where the sets overlap. 2, 0, 2. Or you can just look at your sets and those numbers that we highlighted. Now you take set A along with set B to find the union, and you don't repeat your elements. So A union B. So A along with B is going to give the set that contains 1, 5, 3, 0, 2, 4, 6, and 8. A complement is everything outside of that set A. So you can cover up the elements in there and use your Venn diagram, 6, 8, and 7. Or you can go back to the universe cross out all of the elements from A and then use what's left over. Complement of B, everything outside of that set B. B.
Professor, I have a
5,
question.
1, 3, and 7.
Professor, I have a question.
Inside of a set.
Professor, I have a question. When we are writing the set of A complements C, do we have to write the numbers in order?
One more example, and then we're going to go on to new definitions. Sort of the same ideas.
Maybe just type it in the chat. She probably has her audio off.
So this universe contains letters. Oh yeah, let me see if I'm sorry, I exited the chat. I have my speaker down and I see a hand is raised. Okay, I should be able to hear you. And if you have a question.
Okay, can you hear me?
Yeah, I got you.
When we're writing numbers in the sets of A complements C, do we have to write the numbers in order? Can I put 6, 8, 7, or
Yes.
do we have to? Okay. Thank you.
Sorry, I couldn't hear you. It's good.
No, you're all good.
Okay. Last one for this type is a universe. It contains E, M, P, G, all lowercase. E, little m, little p, little g, R, Y. We're going to stick with A and B as our subsets. A contains M, Y. And B contains R. Same kind of questions, like A intersected with B is one set we'll find. We're going to find the set A, B, A complement, B complement. Okay. I will start with a sketch. Universe. So have A overlapping B. Okay, are there any common elements? No. So this intersection will be empty. In the set A, you have 2 elements. Over in set B is just 1. Outside of both sets, you need the other elements in your space. Got E, P, G, and that's it, sitting outside of both sets. E, P, G. Okay, so A intersect B, we already kind of talked about it from the picture, it's empty. And you can write empty set, or you can write empty brackets. Either one works. Sometimes I think a lot of people put a little comma in there, or just leave it blank. It doesn't matter. I like empty set. A union B is a set A or set B or both. So M, R, and Y are in the union. So the complement of A will not include M or Y. It's everything except for those two elements. So you've got R, E, P, G. Last part is to find the complement of B. So everything except for R. M, Y, E, P, G. That's kind of it for the these specific sets. We're changing it up a little bit, but we're still sort of talking about sets. What I want to say before we leave the problems we've worked on. I guess what I'll say is that every set we've talked about so far has a countable number of elements. So you can count how many elements are in this set, you can count how many elements are in that set, but we're moving into an interval which has an infinite number of elements inside of it, which is not countable. All right, so before we get there, we're going to talk about variables, what kinds of variables there are, and then we'll get into writing values of a variable in interval notation. The first one is to define a variable. It is a characteristic that can assume different values. And we split them into two types. There's one type that can be measured and another that cannot. So if you can't measure the different values, it's a quality and it's a qualitative variable. Qualitative for quality. So they're variables that have values that are not measurements. Something like eye color or political party. One topic. Have your profession or blood type. Like your blood type can be A, B, O, which aren't measurable. They're just they're letters that are possible values of a variable. The other is quantitative variables. Quantitative for quantity. C-A-T-I-T-A-T. They have values that can be measured. If stuff like temperature or height and weight, time. Distances, things like that. Then from the quantitative variables, we can split these up into two types, discrete or continuous. Let's draw a picture first. So over here, we'll have the qualitative variable. Let's put qualitative. Okay. Separate is quantitative variables. From quantitative, we can split into discrete or continuous. Okay, starting with discrete. A discrete variable has a countable number of values. And I think I just have a few examples for discrete variables. And once we get into talking about continuous variables, we'll keep on with that topic and get into interval notation. Okay, first example. So let x be, and x is your variable, so some symbol that represents, it says we use a symbol, and that symbol can be all the different possible values of some characteristic we're looking at. So this time it's the face on a die. The number we obtained when rolling a die. Dice, die. Oh. Okay, so all the numbers that are on the die are 1 through 6. So x can be any number between 1 and 6. X is a discrete variable. So it's any value in the set containing 1 through 6. And I drew a graph. So when I draw this line with arrows on it, which we'll start working with a lot in this class or today's class, this is for every possible real number. So this is going to negative infinity over to positive infinity. And these are all possible values for x. Let's put in some placeholders. Our variable is going to be 1, 2, 3, 4, 5, and 6, and I'll represent using 1 with a solid dot. So 1 is a possible value, so is 2, is 3, 4, 5, 6, but only those values for that variable. All right, next. In this example, a lab has 4 computers. Let X denote the number of computers that are in use during lunch hour. And during that time, x can be any value in the set 0, 1, 2, 3, or 4. So that makes x a discrete variable. So your variable x can take on any value in the set that contains 0, 1, 2, 3, or 4. Either no computers are available, there's 1, 2, 3, or all computers. Okay, we're going to draw a graph. So this is a number line and every single possible number on this line, and we're looking at values of x. We'll put down 0, 1, 2. But the only elements that we're able to use, or the only values that this variable can be, are 0, 1, 2. Okay, a solid dot means you are using that number as a value of your variable. So the last one is kind of the shorter version of what we've been talking about. So x is I'm just going to tell you that x is a discrete variable. Let x be a discrete variable. Such that x can be any value in the set that contains 2, 5, 8, 9. Draw a graph. For your variable. All right, you need one number line for your one variable x. This is where I put my possible values of x. I'm gonna put a 0 over here and then lead up to 2, 4, 6, 8. Place for all of these numbers to go. So we'll have 2 filled in. 5 is right about here. 8. That's it for discrete variables. We'll work with them a little bit, but next is to go into interval notation, which we use for continuous variables. So writing the set of possible values for your continuous variable. So let's write that definition. X is a continuous variable. If possible values of X are in an interval. Or a union of intervals. Cool. So we've got lots of time to talk about interval notation. Getting used to the symbols, or maybe you're seeing these again. You've got a strict inequality like this. Or there's another symbol that looks like that. So this symbol or that symbol are called strict inequalities. These symbols are called. Strict inequalities. So we're going to stick with X being our variable. So for me, it's a lowercase x, but if you use capital X, just make sure you stick with the capital X through the whole problem. Same variable throughout the So that's the goal. But first I'm going to write down what this says. So this says X is less than 3. And there's no equal sign, so it cannot equal 3. So this is an equal sign crossed out, which means X does not equal 3. So you want to find values of X that make that statement true. Something like 2 is less than 3, 0 is less than 3. Any negative number, like -4, is less than 3. Or let's say we can have. Values of X that make this true. So we can have X equal 2. Or you could have X be 0. X equals -5. We talked about how X cannot equal 3. X has to be less than 3, so it can't be a number greater than 3, like X cannot equal 4. just can't go this way. Positive infinity. Past 3. All right, so we draw our number line for the graph. This way is negative infinity. To the right is positive infinity. We want to put 3 somewhere on our graph. X does not equal 3, which means you're going to have an open circle right there and not include that number. So don't. You can just draw over, but I'm going to erase it. Okay, so we've left out 3. We've taken it away. X can be 2 or 0. It can be any number this way. So we can go this way. Maybe extra shooting. We talked about X is not greater than 3, so you're not going over towards the right. You can't include 4 or 5 or 6 or this way. Let's graph X greater than 8. And then write it down first. This means X is any number greater than 8, but not equal to 8, because you don't have an equal sign underneath the symbol. Okay, so X can be 9 or 10, but not anything like 7 or 6 or 5. So to graph this, you put down a number line for your variable X. Place 8 somewhere on the graph. Maybe like 0, 2, 4. X does not equal 8, or X is strictly greater than 8. So we'll take that number away. And use values that make this true. So 9, 10, 11, those make the statement true. All the numbers this way. And don't shade over values that make the statement false. 6 is not greater than 8, so we're not going to include 6 or any of these values. Oh, something.
Question.
Yeah.
For the graph, does it matter how many numbers we put on the graph? For example, like 0, 2, 4, 6, 8?
No, just as long as you have the numbers of interest, like 8.
Oh, okay.
As long as that
Thank
one.
you. Okay.
sorry, I'm getting used to Zoom still and I clicked the wrong button. So we're going to do, we're going to kind of keep here for a moment and graph x greater than or equal to 2. Okay, so we know this one's x. This is for greater than, and you have an equal sign. So or equal to 2. Okay, so this time x can equal to. X can be 3, 5, numbers greater than 2. That's just a few of them. However, x cannot be less than x cannot be any number less than 2. Like I'm thinking right away 1, but even really, really close to 2, like x cannot equal 1.99, things like that. Graph at the top. Okay, so we're going to place 2. Let's put it right here. And we will include 2 and numbers greater than 2. So 2 and greater than 2. But we're not going to shade over 1. We're not going to shade over a number very, very close to 2, like 1.999. So the shaded side is the solution side, and these are not values of x, so these are not solutions. It's not a big deal, but solutions are values of the variable that make your statement true. So just one more example, and then yeah, we can talk about intervals. Okay, we want to graph x less than or equal to 6. Okay, so we've got the equal sign included. So x is less than 6 or x is equal to 6. Let's go ahead and draw a graph. So we have our number line. We're going to place 6. Let's put it in a middle. We do include 6, so it gets a solid dot right over that number. And you need to shade over the solution side. So numbers that are less than 6 are things like 5, 4, 3, 2, 1, negative numbers, everything this way. It's negative infinity. We do not shade over numbers that are greater than 6. So don't include 7 or 8 or 0.0001. So that kind of number is like outside of your solutions. Okay, I think we can at least set up how to write an interval. And then maybe actually do one, but if not, we'll come back and practice next week. Oh no, sorry, not an interval. So intervals are written with rectangular brackets or parentheses. Parentheses, yes. We will put this kind of like those symbols and two numbers inside called endpoints. Smaller number or the smaller endpoint goes on the left side of your interval. Sometimes that value is negative infinity, so it's technically not a number, but it goes, negative infinity would go on the left side because it's very small. The larger number, or if it's not a number and it's positive infinity, that goes on the right. So the bigger value is on the right. Rectangular brackets are used for the greater than or equal to or less than or equal to symbols. We'll say use rectangular brackets. Or less than or equal to, or greater than or equal to. Use parentheses for strict inequalities. Those are the strictly less than or strictly greater than. And then I mentioned it, but we'll write it down. You may work with positive or negative infinity. If you have a negative infinity as an end or a positive infinity as one, like the other end, they always have parentheses because there's not a number that you can actually include. So it's going to have a soft bracket. We can do a couple of these. So we're just gonna, I have a lot of them. So we're gonna try to do at least 2 or 3. We take a set. And, okay, I'm gonna put in a little bit of extra, a tiny bit of extra information. And then we can write our sets the way we were doing at the beginning of class. So what I need to talk about is that number line that we've been drawing for the graph. We'll say it like this. If I don't specify what the variable x is, basically I'm trying to say x is a real number unless I tell you that it's a specific number or specific value. So if x is not defined, I don't tell you exactly what it is, then assume that x is a real number. So x could be countable numbers, 1, 2, 3, 4, 5. X could be fraction, like real numbers include fractions, like decimals, repeated decimals. Like you could have numbers like x could be, I don't want to get too into it, but it could be something like 1.6 with a bar over it. Any number on the number line. The set of real numbers has a special symbol. Okay, so the set of real numbers is denoted by a capital R with a double bar. So you go like double bar to make that capital R. So this symbol is the set of real numbers. So unless I make the universe special, this is the universe we're in our class. Let's let that sink in first. Okay, so before we do examples, any questions or concerns? All right, we want to write the following set in interval notation. So we start the set, and the variable is x. X in the real numbers. So in capital R with a double bar. And put that such that. So x is in R such that x 2 less than or equal to x, which is less than or equal to 5. And that's all we need to do. So what you have, so you have two statements going on. This part, x needs to be, let's see, x needs to be greater than or equal to 2. But also, x needs to be less than or equal to 5. So you draw your number line. Every real number is on this line. And we're trying to represent values of x. I'm going to need 2 and 5 somewhere on the. So one way to solve the problem is to look at that first statement, like I mentioned, x being greater than or equal to 2. So you would include 2 and go greater than 2. Other part is x less than or equal to 5. So you use 5 with a solid dot and go less than that number and equal to. And your solutions for x are the values that make the whole statement true. So it needs to be right here where they overlap and both parts are true at the same time. So we would erase this part and erase that part and just have like this shaded in. Okay, I think that's good. And that's good for the graph, but we need to write this set in interval notation. So right now it's just a set, curly brackets. Let's go here. When you include your number, it gets a square bracket. So for including 2, we go square bracket, it means use 2. Go up to the larger number 5. So 2 over to 5. 5 is included, so it gets a square bracket. X can equal 5. This is the set I gave you. That's the set written in interval notation. Let's do one more, and I think we'll call it good for today. Right? The set of x in R, the real numbers are such that let's do 1 is less than x, which is less than or equal to 2. Start with a graph. Somewhere on your graph, we need 1 and we need 2, but I'll put a little extra. One is not included, so it has an open circle. And you need x to be greater than 1. So you're going from 1, not including 1, and x also needs to be less than or equal to 2. So a solid dot on 2. And numbers less than 2 or equal to 2. So the place where they overlap is where your solutions are. Those values of x make this statement true. And if it were me, I would probably erase the little kind of scratch work and then just put in shading from here over to 2 and include 2. So we have a graph, but we want to write the set in interval notation. So what we have for the set of x in R such that 1 is less than x, which is less than or equal to 2, is the set that starts at 1, your smaller number. It does not include 1. So it goes over to 2. And you can include 2. Square bracket. Okay, so this right here is that set, but written in interval notation. So when we meet on Tuesday, we'll practice writing sets in interval notation and see how far we get. There's no homework right now. I'll post homework 1 next week on Tuesday. So thank you, everybody.